Chapter 13, Section 1, Permutations and Combinations. In Chapter 13, the notes might take you a little bit longer because there's going to be a lot of story problems. There's just not really a fast way to do these examples without having story problems. So the notes themselves might take you longer to write, but I don't think these videos are going to be too much longer than normal. So let's start off with an example. Steve is choosing the 3 courses he's going to take next semester. He must choose 1 math course out of 3 available, 1 science course out of 2 available, and 1 English course out of 2 available. Use a tree diagram to determine how many schedules are possible. And tree diagram is a vocabulary term. Basically, it's just a visual way of showing how many schedules are possible. So, as I'm doing this, I know I have 1 math course out of 3 available. So, let's say I'm going to choose either Math 1, or I could do Math 2, or I could do Math 3. Okay, so I have 3 options for my math courses. It then says I have, what did you say, 1 science course out of 2 available. So I could either, if I choose Math 1, I could either take Science 1 or I could take Science 2. If I choose Math 2, I can then take Science 1 or Science 2. And if I choose Math 3, then I could take Science 1 or Science 2. Okay, then it says I have to choose 1 English course out of 2 available. So if I choose Math 1, then Science 1, I could either choose English 1 or English 2. If I go Math 1, Science 2, then I need to go either English 1 or English 2. If I do Math 2, then Science 1, I'm either going to do English 1 or English 2. And if I do Math 2, Science 2, I'm going to do then English 1 or English 2. Same thing with Math 3. If I do Math 3, Science 1, I'm going to go English 1 or English 2. And if I do Math 3, Science 2, I'm either going to go English 1 or English 2. So the tree itself looks something like this. So here's Steve. Out here on the left, we're going to choose 1 of 3 options for our math. And depending on our math, we've got 2 options for science. And after that, from each science, we're going to have 2 choices for our English. So Science 1 goes to English 1, English 2, Science 2, English 1, English 2. The same thing happens for every one of these. And it's not the greatest. If you do it on notebook paper, it might look a little bit nicer. But with just freehanding this, it kind of looks a little sloppy. But the question then remains: how many possible schedules exist? Well, if I follow 1 and then 2, eventually I'm counting the number of branches down here at the end. So 1, 2, 3, 4, 5, 6, 7, 8, and then I go down here 9, 10, 11, and 12. So your answer then is 12 possible schedules. Okay, so there's your answer. That's how you use a tree diagram. Now, this is a pretty basic example. Tree diagrams, when you have very basic and very limited choices, they're not the worst thing to do. They are not the fastest by any means to do. And I'm going to show you a couple of different ways to do this without tree diagrams. And it's going to go a whole heck of a lot faster. Okay, these 3 choices, the choosing of the math course, the science course, and the English course, are example of independent events. Independent events are events that do not affect each other. So no matter which math course I took, I still had 2 options for science. And no matter which science course I took, I still had 2 choices for the English class. So independent events are events that do not affect each other. So a couple of examples: choosing the 3 classes from the last slide there. Choosing a class would be an example of independent events. Another set of independent events which we'll use more often would be drawing a card, and flipping a coin. Those are events that do not affect each other. No matter what I draw on my card, it's not going to affect what coin or whether I flip a heads or a tails. That's what I mean by that. Okay, the one does not affect the other. If 2 events are not independent, that means they are dependent. Dependent events are simply events that affect each other. A couple of examples of dependent events would be the order in which runners finish a race. Order in which runners finish a race, because if I get first place, I can't get second or third or sixth or whatever. So the order in which runners finish a race, those would be dependent events. The place you get is dependent on what the people in front of you have done or the people behind you are doing. Another example of dependent events that we'll use more frequently would be drawing a card, then another. Whoops, let me spell that correctly. Wasn't even close to right. Then another without, and that's shorthand for without replacing the first one. Without replacing the first card. And we'll get into more independent and dependent events as we go. Section 1 is more of an introductory section. We won't focus too much on independent or dependent. But independent events and dependent events are just a small portion of what's called combinatorics. And really that's what we're going to be studying here. That's what our focus is going to be on in Chapter 13 is combinatorics. Combinatorics is a branch of mathematics that studies different possibilities for the arrangement of objects. When I was in college, I had to take a course over combinatorics, and my professor said basically combinatorics is counting really large things. And I'll show you, we're going to be working with fairly large numbers here in Chapter 13, that it would be really hard to use, especially like a tree diagram like this. It'd be really hard to do this with tree diagrams. So there's formulas, there's examples, there's notes that we're going to do that's going to make things go a whole heck of a lot faster. The tree diagram is a visual representation of the basic counting principle, and you might see it as the fundamental counting principle as well. Either one is applicable. The basic counting principle says this: if one event can happen in P ways and a second independent event can happen in Q ways, then the number of different ways the two events can occur is PQ, or P times Q. And the key word here is independent. If they are independent of each other, then we can use the basic counting principle. So just like this example here with the tree diagram, the math course we took, the science course we took, the English courses we took, those are independent of each other. So we took we had 3 options for math, 2 options for science, and 2 options for English. If we do 3 times 2 times 2, that's 12. Okay, so we could say 3 math times 2 science, and 2 English. 3 times 2 times 2, that is not 24, it's 12. 3 times, this is 4, 3 times 4 is 12 schedules. So that's a real quick way of, or a real quick example of using the basic counting principle. I got another one here for you. Let's just jump right into it. Mr. Thomas has decided to buy a new suit made of either wool or rayon. He has narrowed down the color options to gray, blue, black, or khaki. He will also purchase a matching tie in a floral, striped, or geometric pattern. So, question number 1. Assuming all choices make an acceptable appearance, what are all the choices? Are all the choices for material, color, and tie pattern independent or dependent events? Well, there's a key phrase here. We have to assume that they make an acceptable appearance. So it doesn't matter, what fabric, what color, or what tie we buy. It's all going to go together. Okay, so that's an important part. And because we assume that they all go together, this makes this independent events. We could wear a rayon gray suit with a floral tie, or we could wear a wool black suit with a geometric pattern tie. They are independent events. Okay, so are they independent or dependent? They are independent. The choice of fabric does not affect the choice of color, which does not affect the choice of tie pattern. So, question number 2, how many different suit and tie selections are possible? Well, we have 3 different categories, or 3 different choices we need to make. We need to make a fabric color, or a fabric choice. We need to make a color choice, and we need to make a tie choice, a pattern choice. How many? Let's start back with fabric. So, wool or rayon, to me that's 2 fabric choices. Color choices, gray, blue, black, or khaki, that's 4 color choices. And the tie, we have 1, 2, 3 different options for a tie. So we have 2 fabrics, 4 colors, and 3 ties. What we're going to do is we're going to multiply these 3 together, because that's what the fundamental or the basic counting principle tells us. If the options are independent, the number of combinations possible is the product of all the options for each individual selection. So 2 times 4 times 3, 2 times 4 is 8, times 3 gives me 24 selections, or 24 possible suits that we can purchase. Okay? The title of the section was Permutations and Combinations, and we haven't yet talked about either one. So let's jump right into permutations. A permutation is simply an arrangement of objects in a certain order. And the key here, the order matters. Okay, it's a certain order, it's a specific order. So like ABC and ACB would be two different permutations of the same three letters. Okay, so the notation, when you see notation, you're going to see it two different ways. You can see in the textbook, you can see P, parenthesis, N, comma, N. So what this means, let me write this out for you. This one right here, this one in purple, is the arrangement of all N objects. So if we have 7 coins or 7, whatever, and we want to arrange them, if we want to arrange all 7 of them, it would be P7, comma 7. It would be the arrangement of all N objects. Now, the next one, this N, comma R, this is the arrangement of N objects, taken R at a time, taken R at a time. So if I have, let's say, 7 different coins and I want to arrange 4 of them, it would be P7, comma 4. Okay. In the calculator, you can do permutations, and I'm going to show you how in just a second. It's written slightly different in the calculator. It would be written like this. It would be NPR, capital P, lowercase n, and R in this order. Lowercase n, capital P, lowercase r. Okay, it means the exact same thing as these two, but it's just kind of shorthanded, I guess you could say. But the calculator does denote it like this, so just keep that in mind. Formulas for permutations. If we're arranging all N objects, so P, N, comma N, it's N factorial. So if I have 7 objects, or if I have 7 people and I want to place them in a line, I have 7 options for the first, then 6 options for the second, 5 options for the fourth, all the way down to 1 option left for the 7th. If you're arranging all N objects, your answer, your formula is going to be N factorial, whether it's 7 factorial or 3 factorial or 10 factorial, whatever it might be. N factorial. If we're doing just some of the objects, we're arranging R at a time, the formula is N factorial over N minus R factorial, and that is your formula for permutations if we're not arranging all N objects, whatever it might be. Okay? In the calculator, how you're going to do this, you are going to hit the math button. It's right here, you know where it's at, and you're going to arrow over to probability just like you did for factorial. Option 2 is NPR, and when you hit option 2, you're going to get a screen that looks like this. So if we're going to arrange, if we have 7 objects and we want to do 3 of them, if we want to do permutation, let me try writing that again, permutation of 7, comma 3, what you would type in, you would hit math, arrow over to probability, option number 2 to get this screen, and you're going to fill in, it's going to be 7, capital P, and 3, and then you're going to hit enter, and it's going to do the formula for you. If you want to do this by hand, where you type in 7 factorial over 7 minus 3 factorial in the calculator, you're going to get the exact same answer. Either one, I prefer the calculator just because it's faster and I don't have to remember the formula that way, because I've never come across an issue where I haven't been able to use a calculator, and I'm not going to deprive you of your calculator either. You're going to be able to use calculators on a quiz or test or assignment, so if you can remember the formula, great, but if you remember how to type in the calculator, that'll be good enough. So let's try an example here with permutations. Mr. Waters is arranging his notes binders for pre-algebra, web design, algebra 1, algebra 2, and pre-calc in his cupboard. Assume the binders are placed so the labeled spines are visible. So number 1, is the process of placing the binders a series of independent or dependent events? I'm going to argue that in this case, this is dependent events, and let me explain why. If pre-calc, let's say if pre-calc is placed first, okay, then it can't be placed anywhere else. Then it can't go anywhere else. Okay, so my options for my second binder depend on what I used for my first binder. So if the second choice is dependent upon the first, then the two events are dependent, or the set of events are dependent. So this is a dependent event situation. Question number 2, how many ways can the binders be arranged in the cupboard? Now, this is a Permutations problem, we're arranging all of the binders. So we're going to do this. I'm just going to make 5 spaces. 1, 2, 3, 4, 5. I've got 5 binders, 5 spaces. So my first binder, how many choices do I have? Well, I've got 1, 2, 3, 4, and 5 classes. So my first binder, I have 5 choices. My second binder, I have 4 choices left. I have whatever I picked for my first. My third choice, third, fourth, and fifth. What's going to happen? I've got 3 choices left for my third, 2 choices left for my fourth, and 1 choice left for my fifth. What I'm going to do is I'm going to multiply all of these together. 5 times 4 times 3 times 2 times 1. That sure looks like 5 factorial, and that is 5 factorial. This is 120. So if you want to do it that way, that's one way to do it. Since the order matters here, because it's talking about arrangement, so if I go pre-calc, algebra 2, algebra 1, web design, pre-algebra, that would be different than web design, pre-algebra, algebra 1, algebra 2, pre-calc. Okay, so the order matters. So this is a permutations problem. So we could say 5p5, or we could just say p parenthesis 5 comma 5. This is going to be 5 factorial, which is 120. There are 120 different ways to arrange those 5 binders in the cupboard. Let's try another one here. A high school honor society consists of 7 students. How many ways can all of the students stand in line for a picture? Again, we could list out our 7 spaces just like we did here and multiply them all together, or we can use permutations because the order matters, because we're talking about standing in a line. So if I have Johnny then Susie, that's going to be different than Susie then Johnny. Okay, so the picture is going to look different. So how many ways can all the students stand in a line for a picture? The key word is all of the students. So our permutation is going to be 7 comma 7. We've got 7 kids. We want to line up all 7 of them. If we want to do this with calculator notation, it's 7p7. If we're arranging all of our objects, the answer is going to be 7 factorial. And if you know what 7 factorial, you could write that out as well. That would be 5,040 different ways that you could line up those 7 kids for a picture. Question number 2, how many ways can they elect a president, vice president, and secretary, assuming one person can't hold more than one office? This is where our R value is not going to be the same as our N value. Now we're only electing 1, 2, 3 people out of our 7. So this one, the order still matters, because if I'm elected president, that's different than being elected vice president, which is different than being elected secretary. So the order in which I'm elected definitely matters. So when we do this, we are going to use our calculator again. We're going to use our shorthand notation. So permutations, 7 comma, this time we're not going with 7, we're going 3, because we want to select 3 people in a specific order for president, vice president, and secretary. So if we're going to use calculator shorthand, that's 7p3. If we're going to use the formula, it would be 7 factorial over 7 minus 3 factorial. 7 factorial doesn't really change. 7 minus 3 factorial can become 7 factorial, 4 factorial down on the bottom. You can type this in your calculator several different ways. You could type this one, you could do this one, you could do this one. It doesn't really matter. Either way, you're going to get the same answer in the end. There are 210 different ways to elect a president, vice president, and secretary out of those 7 students. So that's a little introduction to permutations. What I want to talk about now is combinations. And the biggest difference between permutations and combinations is the idea of order. Okay, a permutation, the order matters. And a combination is a selection of objects in which the order they are selected does not matter. That's the key part. The order does not matter to be a combination. So let me show you the difference between permutations and combinations here real quick. So let's assume we're going to select 2 letters from A, B, C, and D. So I'm going to do this. If we're going to do permutations, our options could be AB, it could be BA, it could be AC, it could be CA. Those are all different because the order matters. Okay, we could keep going. We could have AD, DA. What's next? BC, CB. Let's see what's next. BD, DB, and then lastly CD and DC. In permutations, all 12 of those are unique. They are different because the order matters. In combinations, really, you have these two, AB and BA. They're considered the same. Same thing with AC and CA, and AD and DA, or DA, AD. Again, order doesn't matter. BC and CB, they are considered the same. Same thing with BD and DB. BD, and CD and DC the same as well. So in permutations, the order matters. In combinations, the order does not matter. So in combinations, usually our numbers are going to be slightly smaller in comparison to permutations, but we can still get some fairly large numbers as we go along. So notation for combinations, just like with permutations, we had a P out there. With combinations, it's going to be a C. If we're choosing all of our objects, n comma n, there's only one way to choose all of your objects. It's 1. There's only one way. You're not going to see that hardly ever, if ever. You are more likely and much more likely going to see C with n comma r. Again, calculator does the combinations as well, NCR. So lowercase n, capital C, lowercase r. Those are the 3 different ways you would see it notated. Definitely going to be focusing on these 2 with C, n comma r, and NCR. The formula for combinations, you've actually seen it before. It looks like this. The formula for combinations is going to be n factorial over r factorial times n minus r factorial. And what you're going to hopefully recognize is that is the coefficient from the binomial theorem, which gives us the numbers in Pascal's triangle. So we'll talk about Pascal's triangle a little bit more and how we can use Pascal's triangle to do combinations. It works out really, really well. But again, the calculator can do this. If I go back here a couple of pages, the only difference between permutations and combinations in the calculator is you're still going to hit the math button, still going to go over to probability, but instead of option 2, you're going to hit option 3. And the only difference on this screen is it's going to be a C instead of a P, but everything else works exactly the same. If it's permutations, use the option 2. If it's combinations, we're using option 3. So, got an example here for you. In a student council of 20 members, 6 are chosen to be the events committee to plan all the school dances. How many groups of 6 students could be chosen? Now, the order is not important here because if you're on the committee, you're on the committee. There's no head chairman, there's no whatever, there's no treasurer. If you're on the committee, you're on the committee. So the order doesn't matter here, and that's key to note. Order is not important. And if the order is not important here, then this is a combinations problem. Combinations, okay? If it's combinations, we can use our shorthand, we can use our calculators. We're talking combinations, so we've got 20 kids. We're choosing 6 of them. If we want to use the calculator version of the shorthand, it's 20C6. The formula for combinations, 20 factorial, n factorial over r factorial, r being 6, so 6 factorial over 20 minus 6 factorial. If you want to simplify it down a little bit further, it's 20 factorial over 6 factorial times 14 factorial. This is going to be a bigger number. 20 factorial is very large. 14 factorial is still large, but not quite as large as 20 factorial. But again, use your calculator here. Don't work any harder than you have to. The total number of groups is 38,760 possible groupings of 6 to be the events coordinators or the events committee. I've got one more example here. At AP High School, there are 10 names on the ballot for senior class officers. Now, whether that's true or not, I don't know. I just tried to make it a little more applicable to us. At APHS, there are 10 names on the ballot for senior class officers. 4 will be selected. So number 1, how many different groups of officers can be formed? If we're assuming that officers have the same rank, there's no specific role, then this is a combination problem. So we can say order not important. Not important. So this is a combinations problem. Combinations. Okay, so we can say we've got 10 names on the ballot. We're choosing 4 of them. This is something that you can type in your calculator. The other shorthand from the book, 10 comma 4. This is going to be 210. There are 210 different groups of officers for the senior class. Question number 2, how many different ways can a committee be formed if each person has a different responsibility? Now the order matters, because if one person is in charge of, leadership, another person is responsible for, events, then the order in which you're selected matters. So now we can say order matters, or order is important. So this is a permutations problem now. Permutations. Spelled that a little wrong. I'm just writing over it. Permutations. So it's going to be, we still have 10 people. Now we're ordering, or we're picking 4 of them. Again, parenthesis, or P, parenthesis, 10, comma 4 if you're using textbook lingo. The answer here, this is 5,040. So now if the order matters, now our options become a lot higher, because, you know, I could be on the committee and that'd be 210. But if I know I'm going to be on the committee and be in charge of events planning, now that's one of many more possible combinations. The last one here kind of incorporates the counting principle and permutations and combinations. If there are 6 girls and 4 boys on the ballot, how many committees of 3 girls and 1 boy can be formed? What we're going to say here, and we're going to ignore the politics, or I don't say politics, but the social interaction of some groups, some specific people. So we'll say we're going to go on the assumption that choosing the girls and the boys, the girls and boy are independent of each other. Are independent, shorten that, independent of each other. So the choices in our girls does not affect who we choose for the boy. Now we're going to assume that. So what we're going to do is we're going to use the counting principle that we talked about back at the beginning of this video. Use counting principle. Okay, so we don't really want, I'm not going to use a tree diagram. I'm just going to figure out how many options I have for girls and how many options I have for boys. And I'm going to multiply those options together. Now, it doesn't say specific roles. We're just looking for committees of 3. So this is going to be a combinations problem because, again, the order does not matter. I have 6 girls. I need to choose 3 of them. I have 4 boys. I need to choose 1 of them. 4C1, anytime you have a 1 here, it's going to be the other number. There's only one. There's 4 ways to choose just 1 of the boys out of a group of 4. So this is going to be times 4. 6 choose 3, or 6C3 in your calculator. When you do that, that's going to be 20, and 20 times 4 is 80. So if we know we want our committee or our officers to be a committee of 3 girls and 1 boy, we have 80 different options, or 80 different possible combinations of boys, of 3 girls and 1 boy.